Today we are discussing shortest path in a graph from a source node to a destination node. So, shortest path is a very exciting type of topic and there are a lot of algorithms, but most of the people they say that using BFS also we can find shortest path. So let us first of all try to find out what does BFS do. See, breadth first algorithm is an algorithm which finds a path from source node to destination node with minimum number of nodes in between. From source node to destination node with minimum number of nodes in between. Okay, so now what happens if our graph is unweighted graph? Then it will find the shortest path also, because it is finding a path from source to destination with minimum number of nodes in between. And if it is an unweighted graph, then it will become shortest path also. But now if weights are introduced, then it is not able to find the shortest path. It means BFS is not able to find shortest path in case of a graph which is a weighted graph. Let us take an example. Let us consider this graph. Suppose I want to go from 0 to 4. Now if I apply BFS on this graph, so I will be getting a path like this. I will get a path 0 to 1 and 1 to 4. Because this is the only path from 0 to 4 with only one node in between. So if it is unweighted graph, this becomes the shortest path. Now let us introduce some weights to it. Let us introduce some weights to the edges. Suppose this weight is 1, this is 2, this is 3, this is 1, while this is 4, this is 5. Now calculate and tell me which is the shortest path from 0 to 4. Is it 0, 1, 4, 0 to 1, 1 to 4? Total weight will be 9. Okay, total length of the path will be 9. Now if I start this way, 0 to 2, 1, 2 to 1, 2. So 1 plus 2 is 3. 3 plus 5 is 8. 1, 2, 3, 1. So 1 plus 2 is 3. 3, 3, 6 plus 1, 7. So which one is the shortest path? 0 to 2, 2 to 3 and 3 to 1. Although it does not has minimum number of nodes in between. So this cannot be done. If your graph is a weighted graph, then shortest path cannot be found using BFS. So we can't find shortest path using BFS if my graph is weighted. Then what I'll do, I'll use any one of these three algorithms. Dijkstra's algorithm. Dijkstra's algorithm, it does not work for negative weights. It works only for positive weights. Then second one is Bellman-Ford algorithm, and third one is Floyd-Warshall's algorithm. Well, we are taking two examples for shortest path Dijkstra's algorithm. First one is a directed graph and second one is undirected graph with same weights. So these two examples we will be discussing today. Let us implement Dijkstra's algorithm on a directed graph. So we have this directed graph with us and source node is 0. So from 0 we will be implementing Dijkstra's algorithm on this graph. So let us start from 0. Since this is source node, so its distance from itself is 0. All other distances will be initialized to infinite. Then we'll select source node and we'll see what all nodes are directly connected to that source node. So first node which is directly connected to source node, that is from 0, is 1, and distance from 0 to 1 is 3. And distance of 0 is 0 because we are starting from there only. So if I add 3 to 0, then distance of node 1 becomes 3. Since 3 is smaller than infinite, so we will be replacing infinite by 3. Now similarly we'll see, is there any node which is any direct edge from 0? Is there any reachable path from 0 to any other node? Direct. So first direct edge from 0 was to 1. Now there is no direct edge because this edge does not start from 0. Even this edge, this also does not start from 0, and this also does not start from 0. So there is no more edge. So this is our stage number 1. So after completing stage number 1, then we'll see amongst the remaining nodes, that is because 0 we have already selected. Now what are the remaining? 1, 2, 3, 4 and 5. Out of these nodes we'll find which is the shortest distance node. See, one has a distance of 3, all others are having distance of infinite. So 1 is the shortest distance node. So next time, that is second time, we are selecting 1. Now we'll see where all can we go directly from 1. Now from 1 also we can only go to 2. Distance up to 1 is 3. That is distance from source, that is 0 up to 1 is 3. Now from 1 to 2 there is a distance of 2. So total distance up to 2 will become 3 plus 2, that is 5. And 5 is smaller than infinite, so I will be replacing infinite by 5. Is there any other edge from 1? No other edge. Okay, yes, yeah, there is one more edge. There is one more edge from 1. It goes to 3. Now the distance up to 1 is 3. And if I have to go to 3, then I have to add 3 more. So finally it becomes 6. And 6 is smaller than infinite. So what I'll do? I'll replace infinite by 6. So from 1 we had modified the distance of 2 and we have modified the distance of 3 also, 2 also and 3 also. Now we'll go to next stage. Next stage is that we will examine all the remaining nodes. What are the remaining nodes? 2, 3, 4 and 5. We'll examine 2, 3, 4 and 5. And then we find out that the smallest distance node is 2 because a distance 5 is associated with 2. With 3, 6 is associated, with 4 infinite is associated, and with 5 infinite is associated. So next time we are going to select 2. Now what are the reachable nodes from 2? See, from 2, 0 is already processed, so we are not going to consider it. From 2 we can go to 3. Now if I go to 3 from 2, so distance up to 2 is 5. Now if I go to 3, then 5 plus 2, so this distance becomes 5 plus 2. 5 plus 2 is how much? 7. 7 is greater than 6, so we are not going to replace. Okay, so no replacement at this point. Similarly, now what do? We see next. We go to next stage. Next stage there are 3 nodes. What are those nodes? 3, 4 and 5. Okay, we have missed one weight here. Let us include one more weight because so far we are not showing any weight. We are showing a path from 4 to 1, but there is no weight. So let us assume that weight from 4 to 1 is 1. Okay, now next time what we are doing, we are processing 3. Because 3 is having a weight of 6 and all others are having infinite, so we'll process 3. See, whenever we are processing 3, where all can we go directly from 3? We can go to 4 also, we can go to 5 also. Now if we go to 4 from 3, then what is the distance? Up to 3 there is a distance of 6. Now one more will be added and we'll get a distance of 7, which is smaller than infinite. So we'll replace infinite by 7. Same way from 3 we may go to 5 also. What will be the distance associated? Up to from 6 we may go to 5 also. What will be the distance? Not from 6. From 3 we may go to 5. and distance associated from 3 to 5 is 4 and up to 3 is 6. So total distance is 6 plus 4, that is 10. So this infinite will be replaced by 10. Now we go to next stage. In next stage there are two nodes, 4 and 5. So which is having the shortest distance? 4 is having, that is 7. So what do we do next time? Next time we select 4. And where all can we go directly from 4? 1 we are not interested because 1 is already processed, so we will be going to 5. So from 4 to 5 there is a distance of 2. And up to 4 there is a distance of 7. So total distance is 7 plus 2, that is 9. And so far a distance 10 is associated to 5. So we'll replace 10 by 9. So this becomes our shortest distance from our source node, that is node 0. Now what we can do, we can just draw a table. We'll be writing node and shortest distance from source node 0. Node 0, shortest distance, okay, 0 is the starting node, so I'll not start with it. So node 1, shortest distance from 0 is 3. This is the shortest distance, 3. Node 2, shortest distance is 5. Node 3, shortest distance is 6. Node 4, shortest distance is 7. Node 5, shortest distance is 9. So these are the shortest distances from the source node 0, and this we have done in case of a directed graph. So let us apply Dijkstra's algorithm for shortest path on this given graph. So our source node is 0 and the distance will be initialized to 0 because there is no distance from source node to source node. All other distances will be initialized to infinite. Now we'll select 0 and we'll find out what all are the nodes which are directly connected from 0, and we'll modify their distances. See, first node which is directly connected from 0 is 1. Now what is the distance from 0 to 1? 3. So this infinite, because 3 is smaller than infinite, so this infinite will be replaced by 3. Similarly, is there any other node which is directly connected from 0? Yes, 2 is a node which is directly connected from 0. So the distance of 0 is 0 and there is a distance of 2 from 0 to 2. So the final distance up to 2 will be 2, which is smaller than infinite. So we'll replace this infinite by 2. Now we enter into next stage. What does next stage say? Next stage say out of the remaining nodes, which is the shortest distance node. So which is the shortest distance node? This has, 1 has a distance of 3, 2 has a distance of 2, 3 has a distance of infinite, 4 has a distance of infinite, 5 has a distance of infinite. So which one is the shortest distance node? 2, because shortest distance, that is 2, is associated to it. Basically this distance is distance from the source node. So now what we do, we repeat the same thing. What are the nodes which are directly connected from 2? See, 0 is already processed, so 0 we are not going to consider. From 2 I can directly go to 1. Now cost up to 2 is 2. If I go to 1 from 2, then 2 more will be added. So total cost will be, or total distance will be 4, which is greater than 3. So I am not going to replace 3 by 4. Any other node which is directly connected from 2? Yes, I can find a node. node number 3 which is directly connected from 2. So what will be the distance up to 3? 2 plus 2, that is 4, and 4 is smaller than infinite, so I'll replace infinite by 4. Any other node which is directly connected to 2? Yes, 4. What is the distance? 2 plus 2, that is 4. 4 is smaller than infinite, so infinite will be replaced by 4. Now next step. In next step we have node number 1, 1, 3, 4 and 5. So out of these nodes, which is the node which is having the smallest weight? Node number 1, which is having the smallest distance or shortest distance, that is node number 1. So now we calculate distances to all other nodes which are unprocessed from node number 1. So I can, from node number 1, I can go to node number 3. Distance up to 1 is 3. I'll have to add 3 more, 6. 6 is greater than 4, so I won't do it. I won't replace 4 by 6. Now from 1, I can come to 2. Up to 1, but 2 is already processed, I'll not go. From 1, I can come to 4. Distance up to 1 is 3. And if I go up to 4, then what happens? I'll be adding one more distance, so final distance will be 4. We already have a distance 4 there, so I won't be replacing it. Nowhere else can we reach from 1. So now we enter into next step. Next stage, what is our next stage? Now we have nodes 3, 4 and 5. Which one is having shortest distance? I may select 3 also, I may select 4 also. Let me select 3. So distance up to 3 is 4. Now if I want to go to 4, then I'll have to add this 1. So this will become 5, which is greater than 4, so I'll not change. Now from 3, if I want to go to 5, distance up to 3 is 4, and I'll add 4 more, so I'll get a distance of 4 plus 4, 8. So I'll be replacing infinite by 8. Now there are only 2 nodes remaining in next stage. That is node number 4 and node number 5. Which one is having shortest distance? Node number 4. Shortest distance is 4, because I'll compare 4 and 8 only. So now from here, if I go to node number 5, so what will be the distance? Because up to here there is a distance of 4. Up to node number 4 there is a distance of 4. Now if I go up to 5, then I'll be adding 2 more, so this distance will become 6. So this completes our task. Now what we can do, we can prepare a table of shortest distance of all the nodes starting from source node 0. Node 0, shortest distance from source node 0. So I want to write 0 here. I want to find distances of 1, 2, 3, 4 and 5 from 0. Distances of 1, 2, 3, 4 and 5 from 0. So distance of 1 from 0 is 3. Distance of 2 from 0 is 2. Distance of 3 from 0 is 4. Distance of 4 from 0 is 4. Distance of 5 from 0 is 6. Now we have already solved 2 graphs, one directed and one undirected graph using Dijkstra's algorithm for finding shortest path. So now what we have to do? Next thing is quite simple. Now we have to write a program for implementing Dijkstra's algorithm. Now whenever we write a program for implementing Dijkstra's algorithm, very first thing is that what are we going to use? Which data structure are we going to use? So I'll say a min heap will be most appropriate to implement Dijkstra's algorithm, because what is happening in Dijkstra's algorithm, after every stage you have to find the shortest path vertex. Okay, that is a shortest path from the source. So after every stage, for the remaining vertices, you need to find the shortest path vertex. Okay, that you can very well do using a min heap. Now we need to discuss the complexity of Dijkstra's algorithm. Now you know what happens in worst case. Suppose every node is directly connected to all other nodes in a graph where there are n nodes. So worst case, how many updations will be required? Every node is connected to every other node. So every node is connected to n minus 1 nodes. And how many nodes are there? N. So n into n minus 1. See, whenever we find complexity, n minus 1 also means n. So n into n minus 1 or n into n means n square. So this becomes our worst case complexity, time complexity of Dijkstra's algorithm.